डियर स्टूडेंट्स, हम मूव करते हैं अपने नेक्स्ट टॉपिक की तरफ, जो कि है फर्मी एंड बोस पार्टिकल्स। फर्मी और बोस पार्टिकल को समझने से पहले हमें ग्रैंड पोटेंशियल का पता होना चाहिए। ग्रैंड पोटेंशियल क्या है? ग्रैंड पोटेंशियल इज बेसिकली कनेक्टेड विद the grand canonical ensemble that we did in the last chapter. So हम वहीं से इसको कंटिन्यू करते हैं। तो लास्ट चैप्टर में हमने ग्रैंड पार्टीशन फंक्शन कैलकुलेट किया था। दैट वाज summation over j e to the power minus ej minus mu nj over kbt और लास्ट चैप्टर में हमने ग्रैंड पार्टीशन फंक्शन से प्रोबेबिलिटी भी कैलकुलेट की थी। दैट वाज PI that was equal to sum over j. Again I'm using the same summation index. Sorry, here I will not use summation on the top, but instead I will write it like this: e to the power, there is no summation here, e to the power minus ej minus mu n j over kbt divided by the grand partition function. इसको हम इनोवेट करते हैं एज इक्वेशन 2। सो इन दो इक्वेशंस की मदद से हम एंट्रोपी कैलकुलेट करने की कोशिश करेंगे। तो एंट्रोपी के लिए हमारे पास क्लासिकल रिलेशन जो है वो इस तरह से गिवन होता है: एंट्रोपी इन grand canonical ensemble that is S minus KB summation over I PI natural log of PI. So we call this equation 3, and just we have to plug the value of PI from equation 2 into equation 3. Please remember कि ये इक्वेशन वैलिड तब है जब आपके पास एक सिस्टम हो जो कि थर्मल इक्विलिब्रियम और पार्टिकल इक्विलिब्रियम में हो, और उस केस में हम प्रोबेबिलिटी के लिए PI यूज़ करेंगे। सो आई मेंशन इट एक्सप्लिसिटली हेयर। सो दिस इज़ वैलिड when the system is in thermal and particle equilibrium. With a रिजर्वायर. ये रिजर्वायर की बात हमने ग्रैंड कैनोनिकल एंसेंबल में लास्ट चैप्टर में की थी, तो मैं इसको अब ज़्यादा रिपीट नहीं करूँगा. आई विल फोकस ऑन माय कैलकुलेशंस मोर. So we go back to equation 3. And put the value of pi from equation 2 into equation 3. What we will get? S equals minus kb summation over I pi, and when we write log of pi, natural log of pi, then we actually get rid of the exponential. So what we get here is minus ei minus mu ni over kbt minus log of the grand partition function okay. And when we simplify this, what we get is S equals plus kb summation over I pi p sub I e sub I over kbt minus, so we have two minuses here, one minus here, one minus here, and we multiplied with other minus, so we'll get at the end of the day minus sign, and that is minus kb summation over I pi and I over kbt and at the end plus kb, and since there is no summation over log of c, so we write it before and we write just summation over I pi. Okay, so now some things that we know are very obvious. Previously in last semester we used to calculate the average value of something like that. So the average value of energy was used to be summation over I pi ei, and we also calculated the average particle number as summation over I PI and I. And we also know that sum of probabilities is always 1. So what we do, we put all these values into the above equation, and then what we will get, we get the value of entropy S equal to average value of energy divided by T, doing after all the cancellations actually. So we have to cancel KBs somewhere, not T's but KBs, and then we get average of E over T and minus N average times mu over T plus KB log of the grand partition function. We further simplify it and write it as Ts equals E average minus N average times mu plus KB T natural log of canonical partition function, and we enumerate this equation as equation 4. So we write it as equation 4 in this case, as you can see. Okay, so this equation is very valuable for us, equation 4. We have to keep it in our minds. We can even further simplify it actually. So we write it as E average equals, no, not equal to, but okay, E average minus mu times N average minus Ts equals minus KB T times natural log of. So we have just done some rearrangement of this equation. Okay, so we did some calculations in the last semester, and when we calculated free energies. So if you remember what we did last semester, I just remind you a little bit. So we wrote in that Gibbs free energy we used to write was minus KBT log of Z. That Z was used to be our canonical partition function. So on those same lines, we call this thing here on those very same lines, we call this as some kind of potential, this thing KBT log of Z. We call this as grand potential. What we call this? Grand potential. So we call minus kBT natural log of the grand partition function as our grand potential. We denote it with phi g. So our equation number 4 can be written as E average minus mu times n average minus Ts equal to phi sub g. This phi sub g is the grand potential. So if you remember from last semester, whenever we used to define some potential, we could have calculated, we did actually calculate some thermodynamic properties out of this. So here we will do the same thing. So we have now grand potential. We can calculate several thermodynamic properties like entropy, like average number of particles, like average energy, whatever you want. So how we do that? So we put differentials into work. So we write the grand potential. So we can call this equation of grand potential as equation number 5. And we take a differential of 5. So we have d of phi sub g equal to d of E minus d of mu times n average minus d of Ts, and we expand these differentials, the product rule, when we have a composite term inside. So we write d phi g equal to d E average minus mu times d of n average minus n average times d mu minus d ds minus s d t, and we call this equation 6. Okay, now if you remember again thermodynamic section from last semester, we calculated a very well-known relationship that we called the fundamental thermodynamic relationship. Where we used first and second laws of thermodynamics. What was that? That was d of E equals d ds minus p dv plus mu dn. We call this equation 7. So we put equation 7 in 6. So basically we are eliminating dE. So what we get, d phi of g equals d ds minus p dv plus mu dn So here we use average values in fact of n and energy. So and then we get minus mu dn minus d ds minus s dt. So we can get rid of some terms here. Okay, so I forgot one more term here. Okay, that was minus n d mu. Okay, that I forgot. Okay, so we cancel some things out here. So this TDS goes away with this TDS. This positive mu dn and this negative mu dn will also go away. So what we are left with, so we have d of phi g equals minus p times dv minus n times d mu. Remember n average, and then we get minus s d t, and we name it as equation 8. So now we have calculated the differential of this grand potential. Now we are comfortable in getting other values, other thermodynamic relationships from this. So what we do here, so we can determine entropy directly from this relationship, equation 8. From 8 we see that entropy can be written as basically a differential of the grand potential with respect to temperature when we keep chemical potential and volume constants. So we can further write it as partial over partial t k dt log of grand potential. Mu and v are constants here. And what else we can write from this? Actually we can write 2 or 3 things here. So I will just write the average number of particles, that we will write it as the differential of grand potential with respect to chemical potential. When we have other things constant, there is this no negative sign. So then we have volume and temperature constants. So these two relationships we will going to be using more often in next chapters. So we write partial. So we write more specifically as kBT partial or partial mu natural log of the grand partition function, keeping v and t as constants. So basically n average is the average number of particles in any case, depending upon the situation. So we can use these relationships. So in last chapter we did an example, if you remember, we did an example we calculated the average number of particles on a surface which has absorption sites. So some particles can be absorbed on the surface, and we saw that कुछ स्पेसेस में एक पार्टिकल एब्जॉर्ब हो सकता था, और स्टेट हम ऐसे डिफाइन करते थे कि either if one particle absorbed it has an energy EI, and if it does not absorb the surface then we have that energy 0. लास्ट लेक्चर के एंड पे हमने ये एग्जांपल की थी. So we can use the same terminology here. So in that case we calculated surface absorption के केस में हमने एक स्पेसिफिक पार्टीशन फंक्शन कैलकुलेट किया था. मैं इसको z ही लिखूंगा और मैं साथ ये लिख देता हूँ c सरफेस, ताकि आपको कन्फ्यूजन ना हो कि ये क्या है. तो वो था हमारे पास वन प्लस e to the power minus ei minus mu over kBT, sorry, mu ni there was no ni in that. Okay, I minus mu over kBT, ये था हमारा पार्टीशन फंक्शन जो हमने कैलकुलेट किया था surface absorption के केस में. Okay, so we now use that partition function to calculate the average number of particles that we just did an example. We used the average number of particles per site So we calculate average number of particles per site, and that we will do with the formula that we just derived for chemical potential, from chemical potential for the grand canonical ensemble. So that formula is an average this we can also write it like this, the average number of particles per site, और इसको आप कह सकते हैं साइट ऑक्यूपेंसी. ठीक है, दो तरह के नाम आप दे सकते हैं, आप इसको साइट ऑक्यूपेंसी भी कह सकते हैं. So we write it as KVT partial or partial mu one plus e to the power minus ei minus mu over kBT and just we differentiate this equation with respect to mu, and we see that that is kBT times 1 over 1 plus e to the power minus ei minus mu over kBT times e to the power minus e minus mu over kBT divided by kBT. So this will be the differentiation of this term. So what we get here, so this kBT will be cancelled with this kBT, and we get the average number of particles per site as e to the power minus ei minus mu over kBT divided by 1 plus e to the power minus ei minus mu over kBT. Further down, so e to the power minus ei minus mu over kBT, and from denominator we take common factor, and inside the bracket we will get e to the power plus ei minus mu over kBT plus 1, and these things will cancel out, and we are left with an average equal to 1 over e to the power minus ei minus mu, sorry it's not minus, this is plus kBT plus 1. So this is a very important relationship that we should remember to treat the fermions and bosons when we will deal with their site occupancies or average number of particles per site. इसको आप ni कह दें यहाँ से n sub I, because we are using an index I here. So this is very important, and this will help us in determining the energy distribution, or what you call it as the Fermi-Dirac distribution function and the Bose-Einstein distribution function when we study them in detail. So I hope you somehow got the sense of this calculation, and we will discuss further these and some other stuff in the next lecture. Thank you.